Good morning. Welcome to episode number 11 of the ZoomTown Experiment. In today's episode, we're going to be taking a look at the VL53L0X Time of Flight sensor. The reason we need a sensor like this, as you can imagine, if we're going to have, say, 15 Zoomies running around on this layout in ZoomTown, they could easily drive into each other because they're blind. They can't see anything in front of them, to the sides, or behind them. So that is the purpose of this particular sensor, and we're checking it for suitability for our application. Let's take a quick moment to review what we're going to cover today, and then we'll start diving into all the cool details. We'll begin by giving a brief explanation of the TOF, or Time of Flight sensor, and its applications. We'll explain some of the features of this sensor. We'll take a look at it with a practical setup consisting of a schematic and code, and then we'll go into some practical testing. And finally, we'll wrap it up with an analysis of the sensor as it relates to our particular project. Time of flight sensors, for the most part, come in two varieties. You're going to have some form of a light-based system or a sound-based system, usually referred to sound-based systems as sonar. All the light-based ones are typically referred to as time of flight. Now, there are different measurement methods. This particular unit is using a laser. Some use infrared light. It will flash a light, usually in a coded sequence, and then wait for the bounce to return, the reflective light to return to the sensor. This particular sensor operates on the same methodology where it will output a blast of light, laser light, wait for that decoded signal to come back and figure it out. We'll take a quick look at the data sheet for this unit, and I love one of the applications listed right here. It says Robotics, collision avoidance, wall tracking, and cliff detection. That's perfectly for what we need for our application. Of course, it has applications and appliances, access control, liquid level. There's a lot of different things you can do with a time of flight sensor of this type, including digital tape measures. It mentions here in its features that it's a 940 nanometer laser. It uses the ranging sensor combined with an embedded microcontroller to measure the distances and report that data for us to use. It can measure an absolute range up to 2 meters. Our concern is realistically probably not more than 10, maybe 15 inches, somewhere in that range. It is an I2C interface for device control and data transfer. There were a couple other things in here I was going through I wanted to point out. Its operating voltage, of course, very important for us. It's going to be at 3.3 volts, so that works perfectly with the PICO. It's running in fast mode for the I2C interface. Now, as typical of anything with an I2C interface and a lot of different capabilities, there's going to be a very complex exchange of information. And there is a library that I found, and we'll cover that here in a minute. And that makes our job very, very easy. I believe there was something else here a little further down. Bear with me. Okay, this was it here. Ranging accuracy for distance at 120 centimeters, 4%, with a white target, gray target, 7%. This is a little concerning. They're talking about 33 milliseconds, 66 milliseconds. So I'm guessing that is the duration of the measurement. And that can kind of be a problem for our application. We'll see how that pans out in the practical testing that we've got coming up. But the accuracies seem very, very good. There is a difference between the white and the gray. In our case, the Zoomie cars haven't been made yet, so I can really make them any color to suit the needs of the sensor. There is one more diagram here. They're showing kind of the conical measuring, or as the signal goes out and comes back, you're going to have a fanning out or a conical broadcast and reception. And they're saying between, on the emitter, it's about a 35 degrees, and on the collector, about 25 degrees. So that'll give you an idea how much this laser light's going to fan out, which could be a problem, but I don't think in our range it'll be a big issue. And that was kind of it with the data sheet. Very good data sheet, covers a lot of information. And of course, this is very specific to only the sensing device, the laser itself and the sensor. As we're using it here, and I'll have a close-up that you can see this in a little more detail. On the back of the module, there's several resistors, capacitors, and a few other little things that I can't really see with my bare eye very well. But right there is the actual sensor, and we'll give you a nice close-up of this so you can see this in a little more detail. But this data sheet is about that little device, not the whole module. The whole module just kind of brings those signals back to a nice convenient header pin for us to grab that data or provide data to the sensor. When I purchased this sensor, it was $6.99 or $7.99. I looked it up today and it's $9.99, so it's getting pricey. Now, I probably could shop around on Amazon or even AliExpress and get it cheaper, but that's really a real high value sensor, so it's really got to be great for our application to justify that high cost. Otherwise, I'm going to have to look for an alternative device. I didn't have a fritzing module equivalent to this sensor, so I just created this little simple header diagram with the connection nomenclature and showed how I've got it wired up. We've got 3.3 volt coming from the PICO, as well as 0 volts going into VCC for the 3.3 volts, and GND is your incoming 0 volts. SCL is our brown wire coming back to pin 2, and the white wire is going into SDA. And it's going to be kind of hard to see, but we'll just bring it over so I satisfy any criticisms of how it would look. But I've got my header pins on this particular PICO on the back side, and you can see the two pins over here, power 0, SDA, and SCL. And those connect to the header pins on the sensor. And I've got it in this little vise to be convenient for us while we're measuring. And the way this will work, this will be our target. It's just a white box. I picked this because it's not fully gray, it's not fully white, but it's a nice in-between. It's got a flat surface that's clean, and it stands up nicely as we're moving it along to take measurements, because I want to see how accurate this is within our practical testing. Taking a look at the code, this is the library that operates or works with this particular sensor. Got a lot of definitions at the top for various constants and variables, and then we get all the way down. Here's the class for it, all the timeouts, etc., and then all the reading, writing, and all the fun stuff. As you can imagine, writing these sorts of libraries is very difficult, very time-consuming, which makes these things so valuable to us makers, or even professionals for that matter, that somebody takes the time to create these libraries and share them with us. And in this case, this was Kevin McClear, and he has a wonderful number of websites that he operates for YouTube, etc., very much oriented around the PICO environment or the Raspberry Pi environment. Going through our part of the code, we're going to import the libraries that we need from machine, the library for this sensor, some time-related libraries. We'll get the thing set up on the correct pins for I2C interface, And we'll print the scans of the I2C interface so we know what our device number is, or our interface number is. Create the object, our TOF, our time of flight object. From that, it requires a little nap in between power up. So we just go in here, take a little nap. We get to set some settings regarding measuring time budgets and so forth. I didn't really mess around with this a whole lot in my earlier testing. I didn't want to stray too far without having a good reason to do that. Although we may have one, we'll find out here shortly. But this is your pulse period for this one, and as is this one. For our testing, we're just going to get a continuous running loop going here, an endless loop. I'm going to start out, I'm going to assign the current number of ticks in microseconds into ST for start time. This line here is actually making the measurement. So make a note of that. The next line after that is ET for end of time, and again, that's taking a reading from the ticks underscore microseconds. This RT equals time ticks difference calculates the difference between ET, end time, and start time. From that, we've got our measurement of how long this takes to process a measurement. And then we're going to do a little conversion because I'm here in the US and we play with inches. So I'm going to take our range in millimeters, convert that over to inches with 3 decimal places of accuracy, and then we'll print out the results. And that'll be printed out in millimeter and then in inches, and then it'll tell us the runtime to make that measurement. Over here on our test rig, it's really quite simple, crude, but practical. The sensor is currently lined up with this 12-inch long scale. Sorry, folks, this part of the discussion will definitely be all in inches. But from here, I have a scale telling me how many inches away my object is from the sensor. So I can look at the marking here, do the readout over on the program or Thani's shell, if you will, and I can do a comparison between the reading. Now, all these time of flight devices, whether it's sonar or light, visible or laser, infrared, etc., it's going to send out the light will hit here, reflect back, and the sensor will read that light. Sometimes that's an encoded pattern, sometimes it's just a burst of light. There's a good variety of ways that they all handle that information. But it works on just basically the constants, the speed of sound and the speed of light. Pretty well known constants. And from that we can derive very accurate measurements. Of course, the distance from here to here is double, so they're pretty smart. They know to divide that by 2. So let's fire this up and see how we get for behavior. Okay, it's napping, and now it's running. So we'll go all the way up to here. Now, at that point, we should have a reading of about 2 inches, and it's 2.2, maybe 2.3. Not a real big deal there. We could be doing or adding in an offset to take care of that 1/4-inch differential. But it is at 2. This should be at 3. Same offset amount. Four, again that 1/4-inch to 300 thousandths. 5, 6, 7 seems to be creeping a little bit. It seems like we're kind of getting a little more to the 3 and 4 range rather than the 0.23, 0.234. This will be at 8 inches out, and now I'm seeing 0.4, 0.5. 0.45, even hitting some 6s. So it seems to have a little bit of a non-linearity to it. It's fairly consistent, so I'm not going to get too concerned about that. That can be handled in software fairly easy. And in truth, it could also be a variation regarding the lighting that's over here. Now, the other thing that is really catching my eye is right here. You'll notice that that is, if we look at it, we'll say it's 36,000 microseconds, which is 36 milliseconds. That is a very substantial period of time. And perhaps that's where a lot of this might come into play, where we can shorten the pulse periods or these time budgets. Now, this time budget here is remarkably 40,000, which is slightly over this. I'm going to look into this a little more and see if I can find anything there that we could change these values and not affect the accuracy of measurement. Because frankly, for my application right now, I'm thinking 36 milliseconds is simply just way too long. And that will all make more sense once we get the whole thing kind of brought together with all the different sensors and the motor drive and everything else. We need to process time or process all these events very quickly. If we wait too long between events, things change. And this is the perfect example of that. Let's say if I took a measurement here at 36 milliseconds later, once we get the data and process it, this could be this much closer. That could be the difference between a crash or, hey, it's okay, don't worry. Now, I think it's a little bit extreme there, 36 milliseconds. I don't know if it would crash, but hopefully you understand that when we're dealing with motion, there's distance over time. And if we take a measurement at one moment in time, further down in time, in this case 36 milliseconds, our distance is no longer valid that we measured. It's already changed. So we need to get through all these things that the Zoomie has to do in a very quick period of time. If we wait too long, a lot of this data is useless, especially anything to deal with motion. So I'm going to dive into this a little bit more this morning, and I'll see if I can't find some ways to tweak this. If I can, we'll continue forward, but I'm going to hold off wrapping it up for the time being. Welcome back. Well, I was able to experiment a little bit in the past few minutes, and I could get it down to 18 milliseconds for each read, and I'll demonstrate that here. I also went through, because I wanted to get a better handle on this deviation in the measurement. So I set our box at 5 inches from the center and came up with an offset so that we would get a reading of 0, or I shouldn't say 0. We should get a reading of 5 inches. And I wanted to see how the drift is, so to speak. The further away we get, it seems like the error continually gets bigger. So we'll look at two things when I rerun this test here. So we'll get it running. And here you can see we're at 18 milliseconds or 18,000 microseconds. That's a significant improvement from 36, but it's still a lot of time. So I'm a little concerned about that. And I achieved that by adjusting this particular pulse period. That seemed to be the only one to really have a significant effect. Up here, this had no significant effect, nor did this, other than to get me close to this 18,000. So I'm kind of guessing there's two modes here, slow and fast, probably slow for a longer range of measurement, fast for a shorter range of measurements. It's kind of the way I'm figuring out this logic here. But here we can see the distance being measured with the offset, and it's pretty close, reasonably close. I would say it's floating about 3-4 millimeters, maybe less than that, but we're hovering right around 5.0. So let's go out 1, 2, 3, 4. Let's go out about to here, and you'll notice that at that location we've got up to a 1/4 inch or about 6 millimeters of deviation, and averaging about 1/8 of an inch. So it does drift. That could be caused by a number of things outside of my little test environment here. I don't know if I really want to spend more time on this sensor. So my analysis is this. It takes a very long time to read from this sensor and obtain the information we need. 18 milliseconds, although twice as fast as I had it earlier, is still a lot of time. The drift and measurement, in truth, I'm really not looking for absolute precision, but I would like something, even if it's a relative measurement, to be, one, consistent and a little more reliable. So at $10 or $9.99, it's not really making me feel real happy about this purchase. At this time, I think I'm going to put this on the back burner. I don't want to invest a lot more time into this sensor based on what I'm seeing right now. I would rather try to find something that could produce better results at a lower cost, considering I've got 15 to 20 of these Zoomies to build here shortly. So that'll be where I'm going to leave it. At this point, we're going to back burner this sensor, and I'm going to look for something else that might work economically and give me the same kind of feedback with a lot less trouble. So I think this is pretty well going to wrap up this episode. In the next episode, we're going to be taking a look at adding encoders, rotary encoders, to our output motor. Actually, it'll be more involved with the wheel in the output motor. And then it'll allow us to measure movement or relative distance from one location to another very accurately. So hopefully that sensor will perform very well and we'll have a little more forward progress so that we can keep this project a-moving. Thanks for watching, and I look forward to seeing you in the next video.